Hello everyone. Today we'll discuss the solution of gas dynamics and propulsion questions of GATE 2008 paper. So in GATE 2008, total around 20 questions came from gas dynamics and propulsion. Out of them, 4 were of 1 marks question and the rest were all of 2 marks questions. So we'll see the solution of all those questions today in this video. The first question: degree of reaction of an impulse turbine is 1.75, 0.5, and the last option is sorry. And the last option is 0. So degree of reaction of a turbine is defined as enthalpy drop in rotor stage divided by total enthalpy drop in the stage. So, and in case of impulse turbine, in fact, impulse turbine is characterized by the expansion of gas, which only takes place across the stator nozzles, and the rotor blades only acts as a directional vanes to deflect the incoming flow or the direction of the flow. So, in case of impulse turbine, the enthalpy change across rotor is 0. So, for impulse turbine, the enthalpy drop across rotor stage is basically 0. Across rotor is 0. Hence, degree of reaction for impulse turbine becomes 0. So, option D is the correct answer. Second question: in a convergent divergent nozzle of a rocket motor, the wall heat flux is maximum at exit of the divergent portion of the CD nozzle, entry of the convergent portion of the CD nozzle, the throat of the CD nozzle, and midline of the divergent portion of the CD nozzle. Okay, so this is CD nozzle. This is throat of the CD nozzle. And in while flow will take place inside this CD nozzle, the heat transfer between the nozzle and the ambient will take place by means of heat conduction, and the amount of heat will be transferred by means of conduction heat transfer can be written as this K by this formula K del T by del Y, where K is conductivity of the material by which the wall of the CD nozzle is made, and del T is the temperature gradient difference between this wall and the ambient, and del Y is the wall thickness. So this can be written as K T minus TA divided by delta Y, where T is wall temperature of the nozzle of CD nozzle and TA is ambient temperature, and delta Y is wall thickness of CD nozzle. Now, in case of CD nozzle, when the flow enters at the nozzle, it is at very high temperature. So at the entry of the nozzle, the wall temperature is maximum. So T at the entry is highest. So from this, and TA is basically the ambient temperature, which is constant. So, and as this flow takes place inside this nozzle, the kinetic energy, I mean the Mach number of the flow increases, which means the kinetic energy increases. So basically, and this kinetic energy basically comes from the reduction of the flow temperature. So as the flow takes place inside the CD nozzle, the temperature of the flow decreases. and hence the temperature at the entry of the convergent divergent nozzle is highest. So T at the entry of CD nozzle is highest, and as the flow takes place, the temperature gradually decreases. So from this equation we can see Q will be maximum where T is maximum, because TA is constant and delta Y, which is thickness of the wall of the CD nozzle, is also constant. So, and T is maximum at entry of the nozzle, hence Q will be maximum at entry of CD nozzle. So basically this is the correct answer, the entry of the convergent portion of the CD nozzle. Third question. In a scramjet engine, the Mach number at the entry of the combustion chamber is around this, which of the following? So in case of scramjet engine, we all know that the scramjet is characterized as an engine in which the combustion takes place at supersonic velocity. So and in the case of scramjet engine, the inlet, basically this engine, scramjet engine, operates at a Mach number greater than 6. So for case of Mach number 6 to 8, this scramjet operates, and at the inlet the flow enters at a Mach number 6, and then it encounters the diffuser where the compression takes place and the velocity decreases. So after the diffuser, when the flow enters inside the combustion chamber, the pressure is high and the Mach number reduces from what it was at the entry of the diffuser. But in the scramjet engine, the combustion always takes place in the at a supersonic speed. So from the entry, it reduce at the combustion chamber, the Mach number reduces to around 2.5. So in case of scramjet engine, the combustion takes place for 2 to 3, though it operates at a Mach number greater than 6. So this is the correct answer. Next question. Consider steady inviscid flow in a convergent nozzle with a normal shock and divergent portion. The static pressure along the nozzle downstream of normal shock, which of the following remain constant, increases isentropically, decreases isentropically, can increase or decrease depending on the magnitude of the pressure at the nozzle exit. Okay. So to draw the schematic of the CD nozzle, is like this. This is exit of the CD nozzle, this is throat. Now, as per the question, a normal shock is there at the divergent portion of the CD nozzle. So this is the normal shock. And if we plot the pressure, so for this particular flow in the CD nozzle, where our normal shock resides in the divergent portion of the nozzle, the pressure variation of pressure along the CD nozzle will be like this. So it will continuously decrease till the flow in, sorry. So it will continuously decrease till the flow encounters this normal shock. Then it will suddenly experience a pressure jump, and then it will gradually increase till the exit of the nozzle. So at this part, of the nozzle, that is downstream of the normal shock of the nozzle, the flow is completely subsonic. And as this is the divergent portion, so the velocity at this part will continuously decrease till the exit. Continuously decrease till exit, which means pressure will continuously increase till exit, right? So from this part at the downstream part of the normal shock, pressure will continuously increase, and the downstream part, this downstream of the normal shock part, this part is isentropic. So no loss is taking place downstream of the normal shock part of the nozzle. So the correct option will be, it increases isentropically to the static pressure at the nozzle exit. Option B. Next question. The supersonic wind tunnel design. In supersonic wind tunnel design, an oblique shock diffuser is preferred over a normal shock diffuser because it reduces total pressure loss. The flow is slowed down more rapidly. The flow is accelerated more rapidly. It increases total pressure loss. Okay. So if we draw both the cases where the so if we just draw both the schematic of both the cases, the normal shock diffuser and the oblique shock diffuser, this will be the following. So this is the normal shock diffuser. This part is the test section of the wind tunnel where the Mach number of the flow is supersonic. And of course, this is the exit of the wind tunnel where the flow is being discharged, and the Mach number is obviously uh, very subsonic, very slow. And pressure at this is atmospheric pressure, which is 1 atmosphere. So this is the normal shock diffuser. And now if we see the oblique shock diffuser, So again, for this also, this is the test section where the flow is supersonic, and this is oblique shock diffuser. So here the flow deceleration takes place by means of multiple oblique shock, which with a terminating normal shock. This is a terminating weak normal shock, and this, of course, where the flow is being discharged. So the Mach number here is very less, and pressure is atmospheric pressure. Now, at the test section of the wind tunnel, the flow is supersonic, and at the exit, it has to be discharged at an atmosphere at a very low Mach number. So this reduction, this deceleration of the flow has to take place in a way that the pressure loss in the flow is minimum. So for if we compare this case where the flow is being decelerated by means of a normal shock with this where the flow deceleration is taking place across multiple oblique shock which ends with a terminating normal shock, the pressure loss across this oblique shock is always less compared to a normal shock. And as our criteria of the flow, as our criteria to discharge the flow is that the flow has to discharge in a way that the total pressure loss is minimum. So we always go for this one because across the oblique shock, the total pressure loss is always less compared to that of a normal shock. So the correct answer is the reduction of, it reduces the total pressure loss. And the for same upstream Mach number, total pressure loss across a normal shock is always higher compared to that of across a series of oblique shock with a terminating normal shock. So for this reason, we always choose this oblique shock diffuser for supersonic wind tunnel design. So the correct answer is it reduces total pressure loss. Next question. Consider a 2D body in supersonic flow with an attached oblique shock as shown below. So an increase in the free stream Mach number m infinity will cause the oblique shock wave to move closer to the body, detach from the body, move away from the body, become a normal shock. So this is the body, which is basically a wedge which is kept in a supersonic flow, and as the flow is supersonic, so as the flow is supersonic, so oblique shock will form. Oblique shock will form at the edge of the wedge. Now, if we increase the free stream Mach number m infinity, so what will happen to these oblique shocks? So the answer will draw by from the theta beta m plot of the flow. So the theta beta m plot for the oblique shock is as follows. So theta is basically deflection angle. This is theta, and beta is the wave angle. This is beta. So this is oblique shock wave angle. Now the theta beta m relation for different Mach number of the flow is as following. So this is the theta beta m relation for a particular Mach number, let's say m1, and this is the theta beta m plot for a particular Mach number m2, and m2 is greater than m1. So as we go this way, the Mach number increases. Now in our case, the theta remains constant and m is increasing. So if we do so for same theta, m1, from this plot we can see that m1 gives higher shock wave angle beta 1 compared to m2. This is beta 2. So from this plot we can conclude that keeping theta same, that is the wedge angle or deflection angle same, if we increase the free stream Mach number, the shock angle decreases, because from here we can see that beta 2 is less than beta 1, which means for higher Mach number, for the higher higher free stream Mach number, the oblique shock wave angle will be less compared to that of the lower free stream Mach number if the deflection angle remains same. So the correct answer will be, so as the beta is decreasing, which means the oblique shock wave will move towards the body. So it will, as m increases, the shock will move towards the body. So move closer to the body. This is the correct answer. Next question. A turbofan engine has a bypass ratio of 5 and a total mass flow rate of 120 kg. The mass flow rate through the bypass duct. Okay. So the bypass ratio of a turbofan engine is given as the mass flow rate through the bypass nozzle divided by mass flow rate through the core engine. So the bypass ratio of a turbofan engine is given as a ratio of mass flow rate through the bypass nozzle and the mass flow rate through the core engine. So for this given problem, this bypass ratio is 5 and the total mass flow rate is 120. So m total is equal to ma bypass plus ma core. This equal to 120 kg per second, and we have to find out the mass flow rate through the bypass duct. So from this, for this particular problem, you can write it as equal to 120. So if we solve this equation, we'll get as the bypass mass flow rate will be 100 kg per second. B is the correct answer. Next question. A turbojet engine is operating with afterburner off. If the afterburner is switched on, then both thrust and thrust specific fuel consumption decreases, thrust increases, thrust specific fuel consumption decreases, thrust decreases, thrust specific fuel consumption increases. Both of the thrust and thrust specific fuel consumption increases. Now, in case of turbojet with afterburner, so afterburner is basically used to get higher thrust, but this thrust comes with a cost, and the expense of getting this high thrust is the high fuel consumption. So in case of turbojet with afterburner, for turbojet engine with afterburner, we get high thrust at an expense of high fuel consumption. High fuel consumption. So, and as thrust specific fuel consumption is given by m dot by T, so SFC also increases in case of turbojet engine with afterburner. So for this turbojet engine operating with afterburner on, both thrust and SFC increases. Both thrust and SFC increases as this higher thrust is obtained at an expense of very high fuel flow rate. So C is the correct answer. Next question. Ideal ramjet engine is flying at a Mach number m. The exhaust gas static temperature at the outlet of the nozzle is TE, and the ambient static temperature is TA. The gas constant is R. The specific heat ratio is gamma, do not vary with, which remains constant throughout the ramjet. Assuming that nozzle exhaust static pressure is equal to the ambient pressure and fuel ratio is less than 1, the thrust per unit mass flow rate is which of the following? Okay, so for a ramjet engine, the equation of thrust can be given by this equation. So this is the thrust which is produced by the exhaust gas, and this is the pressure thrust. So here ma dot is the mass flow rate of the air through the engine, and mf dot is the fuel flow rate, and ui is the inlet velocity of the gas in the engine, and ue is the exhaust velocity, pa is the atmospheric pressure, pe is the static pressure at the exit of the nozzle, ae is the nozzle exit area. Now in this case, for ideal cases, we will consider that pa equal to pe. So here in this case, no pressure thrust is there, so this part is 0. So this F, the thrust produced by the engine, becomes ma dot 1 plus mf dot by ma dot ue minus ma dot ui, and this part becomes 0. So F by ma dot basically becomes 1 plus F ue minus ui. So here F is equal to ratio of mass flow rate, fuel flow rate with mass flow rate of the air. And as F is less than 1, so 1 plus F is almost 1. So F by ma dot is ue minus ui. So from from that F by ma dot ue minus ui. Now this ue can be written as the exit Mach number into the velocity speed of sound at exit of the nozzle, which it can further be written as root over gamma or Te, where Te is the nozzle exit static temperature, R is gas constant, and gamma is ratio of specific heat. So substituting that from in this equation gives me root over gamma R Te minus ui. Now this ui is the velocity of the flow at the entry of the engine. So this ui can again be written as m into root over gamma rt. Sorry. So this ui can be written as m into a, where m is the Mach number at which the flow is entering into the engine, which means the Mach number at which the aircraft is flying, multiplied by a, which is the speed of air at the entry of the engine. So this can be written as root over gamma r ta, t or ta, or this t is basically the ambient temperature. So substituting that in this equation, minus m into root over gamma rt. Now, as the Mach number at which the flow exits the nozzle, and the Mach number at which so here me is the Mach number at which the flow exits the nozzle, or the exhaust Mach number of the exhaust gas, and m is the Mach number at which the aircraft flies, and me equal to m. The exhaust Mach number is equal to the Mach number at which the aircraft flies. So from this equation, we can write root over gamma rt, take common, and as me equal to m, so this will simply give us root over pe by ta minus 1. So this is the equation of thrust produced by mass flow rate. So this is the equation of thrust produced in the ramjet engine. So this is the correct answer. Next question. A 50% degree of reaction axial flow turbine operates with a mean blade speed of 180 meter per second. The flow leaves the stator and enters the rotor at an angle 60 degree of the axial direction. The axial velocity is 150 meter per second and remains constant throughout the stage. The turbine power per unit mass flow is okay. So if we draw the velocity diagram in this axial flow turbine, it will be like this. So this is the fixed blade, or the stator part of the axial flow turbine, and this is the rotor blade. So C is the this is CA, which is axial velocity, and C axial velocity remains constant throughout the stage. C is the absolute velocity, W is the relative velocity, and U is the blade velocity. So what is U? U. Okay. This is tangential component of W2, and this is tangential component of the CP of C3. Beta 2 alpha 2 Now, as per the given information of these questions, the degree of reaction is 50%, and the axial velocity is 150 meter per second, which remains constant throughout the stage. The blade velocity is 180 meter per second, and alpha 2, which is the rotor entry angle, is 60 degree. And we have to find out the turbine power per unit mass flow rate. Now, for degree of reaction 50% degree of reaction, we know that alpha 3, which is this, is equal to beta 2. For 50% degree of reaction. And the stage work in axial turbine is given as stage work of axial turbine is given as this W equal to U CT2 plus CT3 which can be this CT2 is this part, this velocity. So this CT2 can be written as C2 tan alpha 2 plus CT3, which can be written as C3 tan alpha 3. Sorry. So CT2 is this velocity, CT2. So this is nothing but CA tan alpha 2 from this triangle. So this can be written as CA tan alpha 2, and CT3 can be written as CA tan alpha 3. So U CA tan alpha 2 plus tan alpha 3. Now alpha 2 is given as 60 degree and we need to figure out alpha 3 to get W. So from this triangle, this WT2 is the tangential part of the relative velocity, which is this WT2. This can be written as CT2, which is this entire part, minus U. U is this. So WT2 can be written as CT2 minus U. Minus, and CT2 is nothing but CA tan alpha 2 minus U. Now CA is given as 150, tan of alpha 2, which is 60 degree, minus 180 meter per second. So this comes around 79.8 meter per second. And WT2 is also equal to CA tan beta 2 from this triangle. We can see that WT2, the base of the triangle, is CA tan beta 2. So this is nothing but CA tan beta 2, and CA is given as 150 meter per second. So from this we get beta 2 equal to 28 degree, and for 50% degree of reaction, the beta 2 is equal to alpha 3, which is equal to 28 degree. Now substituting this in this equation, we get that W equal to U CA tan of alpha 2 plus tan alpha 3, which is equal to 180, 150 tan of 60 degree plus tan of 28 degree. So this joule per kg, and this will come something around kilojoule per kg. So this is option D is the correct answer. The power produced per unit mass flow rate is 61.13 kilojoule per kg. Next question. The chamber stagnation temperature inside a rocket motor is Tc. Only a conversion nozzle is used and the flow at the exit of the nozzle is choked. Assume that the nozzle exhaust static pressure is equal to the ambient static pressure. Gas constant for exhaust gas is R and ratio of the specific heat is gamma. The specific impulse of the rocket motor is which of the following? Now, for a rocket motor, the equation of thrust is given as m dot ue plus so this is the thrust produced by the exhaust gas and this is pressure thrust. Now, for optimum expansion, PE will always be equal to PA. Hence, by this part, no thrust will be. This part will not have any contribution in the thrust, total thrust. So for this, as in this case, we are considering P equal to PA. So F will be equal to m dot UE, where m dot is the mass flow rate of the exhaust gas and UE is the velocity of the exhaust gas. So from this we get F by m dot is UE, and this is the specific impulse equal to F by m dot, which is equal to UE. Now UE is can be written as MEAE, where ME is the Mach number of the exhaust gas and AE is the speed of sound at the exit of the nozzle. So this can further be written as root over gamma RTE, where TE is the static temperature at the exit of the nozzle. And as it is said that the nozzle is a conversion nozzle and it is choked. So for conversion nozzle, this is exit and this is so in case of conversion nozzle, for choked flow, the Mach number at the exit is always equal to 1. So for conversion nozzle, for choked flow, Mach number at the exit of the nozzle is 1. So basically the flow is sonic flow at the exit when the nozzle is choked. So from here in this question, as it is said that the Mach the nozzle is choked, so ME will be 1 and it will be root over gamma R TE. So UE is nothing but so it can be written as TC into T by TC, because both TC get cancelled and we will get this equation. So a TC is nothing but the chamber pressure. So and from the isentropic relation of the nozzle, we get that TC by TE is nothing but 1 plus gamma minus 1 by 2 m square. So So as the flow inside the convergent nozzle is isentropic, so the chamber pressure or the total pressure of the total temperature or the chamber temperature of the flow will remain constant throughout the nozzle. So this Tc remains constant throughout the nozzle, and hence by employing this isentropic relation, we can say that Tc by Te is nothing but 1 plus gamma minus 1 by 2 m e square. And as me is 1 for the choked flow, this becomes nothing but 1 plus gamma minus 1 by 2, which is nothing but gamma plus 1 by 2. So by substituting this in this equation, what we get is root over gamma r Tc to 2 by gamma plus 1, which is nothing but root over gamma r Tc divided by gamma plus 1. So this is the correct answer. Next question. Air enters the combustor of a gas turbine engine at a total temperature of this and leaving the combustor at a total temperature of this. If Cp remains constant at this, the heating value of the fuel used is this, the fuel to air ratio. Okay. So if this is the combustor, the combustion chamber, this is entry of the combustion chamber, this exit of the combustion chamber. So the total temperature at the entry of the combustion chamber is TO1, and total temperature at the exit of the combustion chamber is TO2. The mass flow rate in the combustion chamber is MA dot, and the mass flow rate and the fuel flow rate inside the combustion chamber is MF dot. Now if we apply a energy balance equation across this combustion chamber, so the total energy, the entry and exit will remain constant, will remain same. So by employing the energy conservation equation, what we get is, so the total energy at the entry of the combustion chamber is MA dot TO1, and the total energy addition into the combustion by means of addition of fuel is nothing but MF dot CV. So CV is the calorific value of the fuel. So this will be equal to the total energy of the flow at exit of the combustion chamber. Right. Now, from the question, as per the given information, the TO1 is 500 Kelvin, TO2 is 1800 Kelvin, Cp is 1.005 kilojoule per kg, and Cv is 44 megajoule per kg. And F is the ratio of fuel flow rate with the mass flow rate. So if we take common MA dot from both the side, it becomes TO1 plus F CV equal to 1 plus F TO2. Now substituting all this equation, we get, so 44, this is megajoule per kg, we have to convert it into the joule. So we have to multiply it with 10 to the power 6 equal to 1 plus F into 1800 kilojoule. Okay, 1800. So by solving this equation, we get F equal to So this will give us something around this. So this is the correct answer. Next question, the initial temperature sensitivity of burn rate of a solid rocket motor propellant is positive. If the initial temperature increases, then thrust increases. So if the initial temperature increases, what will happen to the thrust and the burn time? So since the initial temperature sensitivity of the burn rate is positive, the burn rate will increase with increasing initial temperature. Since the initial temperature sensitivity of burn rate is positive, the burn rate will increase with increasing initial temperature. Now, as the burn rate increase, as the burn time is basically inversely proportional to the burn rate. As burn time is inversely proportional to burn rate, hence as burn rate increases, burn time decreases. And as the burn rate increasing, burn rate is increasing, which means the mass flow rate of the exhaust nozzle of the exhaust gas will be increasing. So, and which basically means the kinetic energy of the exhaust uh, gas is increasing, and that will in turn increase the thrust of the thrust produced by the rocket motor. So for this case, as the burn rate is increasing, the thrust will also increase, and the burn time will decrease. So this option A is the correct answer. So the explanation of this is, as the initial temperature sensitivity of burn rate is positive, so burn rate will increase as the initial temperature increases, and as the burn time is inversely proportional to burn rate. So if burn rate decreases, burn rate increases, burn time will decrease, and as burn time increases, the mass flow rate of the exhaust gas increases, which means the kinetic energy of the exhaust gas increases, which in turn increases the thrust. So thrust will increase, but burn time will decrease. Option A is the correct answer. Next question. The aircraft is cruising at a Mach number 0.8 at an altitude where the ambient static pressure is this, the diffuser exit total pressure is this. Assuming there is no change in the specific heat or constant pressure across diffuser, the ratio of the specific heat is this, the adiabatic efficiency of the intake. Okay, the adiabatic efficiency of the intake is okay. So if we draw a TS diagram of flow in diffuser, this is the ambient condition. This is the entry of the nozzle. Two denotes the exit of the nozzle. and 2s denotes the isentropic. The isentropic, if the flow was isentropic inside the diffuser, so that condition is noted by S. This is P2, and so this is the total pressure at the ambient, the atmosphere. This is total pressure at the exit of the nozzle. This is static pressure at the exit of the nozzle. This is static pressure at the exit of at the entry of the sorry, not nozzle, it is diffuser. So this is static pressure at the entry of the diffuser, ambient static pressure, exit pressure at the of the diffuser, the total pressure at the exit of the diffuser, total ambient pressure. And this S, the condition denoted by S, is basically the isentropic condition. So if this is the TS diagram of the flow inside the diffuser. Now the efficiency, diffuser efficiency, is given as HO2, the total enthalpy, isentropic enthalpy at the exit of the nozzle, enthalpy at the ambient, total enthalpy at the atmosphere, so this Cp is constant, so Cp gets cancelled in both numerator and denominator. And if we take Ta common in both numerator and denominator, it gives TO2 is divided by Ta minus 1 by Ta minus 1. Now TOA by Ta, this can be given as this from isentropic relation of gases is m square, where m is the Mach flow rate at which the aircraft is cruising, which is given as 0.8. So Mach is basically 0.8. And this TO2s by Ta, this can be given as from isentropic relation of gases. This is total pressure at the exit of the diffuser divided by pressure at the entry of the diffuser to the power gamma minus 1 by gamma. So if we just substitute this in the equation of eta d, so this simply gives us plus gamma minus 1 by 2 m square minus 1. So this gets cancelled, and this becomes, so PO so PO2 is given as 140 and PA is 95. So it will be 140 by 95 to the power divided by 1.4 minus 1. by 2.8 square. So if we calculate this, it will come something around 0.9153. So this is the correct answer. Next question. A liquid rocket engine with oxidizer to fuel ratio 5:1 produces a thrust of 1 meganewton. The initial mass of the rocket engine is 100,000 kg and its mass at burn out is 10,000 kg. The characteristic velocity C star and the thrust coefficient CA for the engine are this respectively, and you have to find out the mass flow rate of the fuel, and in the second case the initial velocity of the rocket is given and the velocity of the rocket at burn out we have to find out. Okay, so the given informations the oxidizer to fuel ratio. So oxidizer to fuel ratio is 5 and the thrust is 1 meganewton, which is 10 to the power 6 newton, and the initial mass of the rocket is 100,000 kg and the mass of the rocket after burnout is 10,000 kg. Characteristic velocity is and thrust coefficient is 1.4. The mass flow rate of the fuel we have to find out. So the thrust produced by the rocket can be written as PCATCA, where PC is the chamber pressure, AT is the area of throat of the CD nozzle, convergent divergent nozzle, and CF is the thrust coefficient. So, and also this m dot, the mass flow rate, so m dot is PCAT C star. So from this equation can write PCAT as m dot C star CF. So this will simply give m dot as T divided by C star CF 10 to the power 6 divided by 6 1.4. It's nothing but 299 kg per second. So this is mm dot. So mf dot is the mass, denotes the mass flow rate of the nozzle, and the mass of the rocket is denoted by capital M. Okay, so MF dot is the fuel flow rate is 299.36 kg per second. So this is the correct answer. And for the second part, neglecting gravity and drag effects, if the initial velocity of the liquid rocket engine is 2.5 km per second, the velocity of the rocket at burnout. So CJ, the exhaust gas, the speed of the exhaust gas can be written as T by m dot, which is nothing but 10 to the power 6 divided by sorry, I made a mistake here. So it is asked that the mass flow rate of the fuel. No, it's okay. So this T by m dot, so this gives something around 3340 this, and the increase in the exhaust velocity due to burnout is given as given by this formula. So by substituting the values, we get so this will come something around and the initial velocity of the rocket engine is given as is 25.2.5 kilometer per second, which is 2500 meter per second. So the final velocity is 500 plus the delta V. So this will come something around 10.19 kilometer per second. So this is the answer. This. Next question, a multi-stage axial flow compressor operating at an adiabatic efficiency 0.9 develops a total pressure ratio of 11. The total temperature at the inlet to the compressor is this, and the stagnation enthalpy rise across each stage is this. The ratio of the specific heat is this. Specific heat at constant pressure is this. Total temperature rise across the compressor we have to find out. And the second question, the number of stages we need to find out. So if we draw the TS diagram of the flow across a compressor, it gives something like this. And this S denotes the condition if the flow was asymptotic. So the eta C, that is the efficiency of the compressor, can be given as TO2S minus TO1 by TO2 minus TO1, where TO1 is the total temperature of the flow at the entry of the compressor, and TO2 is the total temperature of the flow at the exit of the compressor in the real case, and TO2S is the total temperature of the flow at the exit of the compressor if the flow was isentropic. So by taking common TO1 from both numerator and denominator, it gives -1 divided by TO1 -1. And from isentropic relation, this TO2s by TO1 can be written as pressure ratio. So TO2s by TO1 can be written as PO2 by PO1 to the power gamma -1 by gamma, and this PO2 by PO1 is nothing but pressure ratio. So this will be nothing but this pressure ratio is given by as 11, and this pressure ratio is 11. So this is nothing but so by solving this equation, we get TO2 by TO1 as 2.09, which basically gives TO2 as, and TO1, which is the total temperature at entry of the nozzle, is given as 335. This is given in the question. So this will be 2.09 multiplied by 335 Kelvin, which is nothing but 330. So this will be 701.26 Kelvin. Hence, total temperature rise across this nozzle will be equal, across this compressor will be equal to TO2 minus TO1, which is minus 335 Kelvin. So this is nothing but 366.26 Kelvin. So this is the correct answer. And for the second part, the total temperature, total number of these stages, compressor stages required are. So the total temperature rise per stage is given, which is, so total enthalpy rise per stage is given as 37. So total temperature rise per stage is CP to Kelvin, which is equal to 36.81 Kelvin. And as we have obtained that total rise in the total temperature in the entire stage is this value. So the number of stages are this total rise in the total temperature divided by rise in the total temperature in a single stage. So this will be which is equal to, so this is nothing, this will come something around 10. So the total number of stages required are 10. So this is the correct answer. Okay, so these were the questions from gas dynamics and propulsion in K 2008, and we have seen the solution of all the questions. Thank you.